Hi guys, welcome to this lesson. In our previous lesson, we spoke about the intro to the number systems and we look at the various number systems. In this lesson, I'm going to take you through natural numbers. We'll delve deeper into what natural numbers are, the properties, and some special things you have to know about natural numbers. So, when you say natural numbers is just a simple category of numbers, and literally they are known to be the first mathematics humans invented, right? So generally natural numbers are represented with a capital N but with a double slash in the middle, right? So this is the general representation of natural numbers. So natural numbers are a group of numbers that admits a minimum number of 1. So every natural number admits a minimum number of 1, right? Yeah, so for the natural number sets, it starts from 1, then 1 adds to itself 1 plus 1, then we have 1 plus 1 plus 1. So that gives us 1, 2, 3, then to infinity. So popularly, natural numbers are called counting numbers because in our usual communication, we make use of 1, 2, 3. The basic numbers we use is simply what we call the natural numbers. Now, let's go straight to the operations of natural numbers. Natural numbers operate under addition and it satisfies the property called closure property. Closure property. Closure property will be specially captured in the subsequent tutorials. When we talk about closure property, what this means is a property that defines numbers such that when you perform an operation, the result of that operation should be found within the set of numbers. So as you know that natural numbers start from 1, 2, 3, 4 to infinity. If I perform addition of any two of these natural numbers, say 2 plus 3, I'm supposed to get 5, and 5 is a natural number. Hence, we say that addition is closed under natural numbers, right? So one of the operations we can use in natural numbers is addition. We also have multiplication, and natural numbers is also closed under multiplication, so that if I have 3 times 5, I'm going to get 15, right? And 15 is a natural number. So this is also satisfying multiplication. Now, a special case what you call division. We realize that if I have 2 and I divide it by 3, my result is not going to be natural. Hence, division is not closed under natural numbers. Okay, so natural numbers are said to be discrete. So the term is discrete. Discrete means that it has fixed values. If I have 1, I'll jump to 2, I'll jump to 3. I don't have any numbers within this intervals. Okay, so they are layers, or let's say, yeah, they are layers. Let me say it that way. Now, there is a special property I would like to introduce to you, which we call the Euclidean division. Euclidean division. Since natural numbers doesn't satisfy or is not closed under division, but it has this property called Euclidean division. Euclidean division is simply having a number a to be equal to b times q plus r, where r is less than b. What does it mean? If I have a number and I can decompose it into a multiplication factor and an addition factor, then I can say that it's satisfying the Euclidean division. Now let's say something. If I have 15 is the same as what? 2 times 7, right? Plus what? 1. I don't know if you get it. Yeah, so 2 times 7 is what? 14, plus 1 is what? 15. So in a way, we have divided 15, but not the usual division. That's why we call it Euclidean division. And that is what natural numbers is satisfied on, right? So we move on to some special properties of natural numbers. So let's talk about some special properties of natural numbers. So generally, natural numbers straight away satisfy what we call the commutative property, right? So the commutative property, so commutativity, right? So commutative, which is very fundamental. If you have a commutative principle being shown, you have a plus b should be equal to b plus a, as simple as that, right? So if I have 2 plus 3, the order doesn't matter. 3 plus 2 is also the same. quickly, it also have the associative property, right? Associative property is simply you have an A plus B plus A, or let me say A plus B times C like this. You are going to simply have something like um let's say no, let me change this. Yeah, so for associative property, let me use a simpler way. You may have A plus B or plus C, right? Now this can also be said A plus B plus C, so it's still the order doesn't change, right? Then we have distribution over addition. Distribution over addition, right? Or over addition. So what do that mean? If you have A multiplying B plus C, then I can distribute this to give me AB plus BC. So these are some few properties which you're looking at, and we'll be looking at several properties. Now, when you talk about identity in natural numbers do not have, so take note of this. Natural numbers do not have additive identity. Additive identity. What I mean by additive identity is that there is no special redundant number. An identity is just a number which, when you add anything to it or itself, it doesn't affect the number you're adding. So typically, the number which should have been the additive identity of natural numbers is what, zero. But you know that zero is not a natural number in this sense, right? Hence, natural numbers do not have additive identity, but it has multiplicative identity. So natural numbers have what you call multiplicative identity, and that is what, 1. If I multiply any number by a 1, what do I get? I get the number itself. So that makes it satisfy this rule, right? The natural numbers are well ordered. They are very well ordered. So we will talk about the principle of well ordering in our subsequent tutorials. But now let me show you something. If I have 1, I move to 2, I move to 3. You realize that it's increasing and never ends, right? And this is the idea of well ordering. So natural numbers, you write this natural numbers, a set where you have your natural numbers n here, comma, less than or equal to. So this is the principle of well ordering here. So all natural numbers starting from 1 to infinity are associated with what, less than or equal to. If I have any two natural numbers, there is a smaller number, then there will be a bigger number. So you cannot have 3 greater than 2. It destroys the order. Okay, so that is it. Now, having talked about this, let me give you the few stuff you should know. We call it the piano axioms of natural numbers. Piano axioms. Okay, so what are the piano axioms? So these are few stuff that I'm going to show you, and these axioms were invented by who we call Giuseppe Piano, right? He was a very famous mathematician, and he stated these few stuff during the evolution and the beginning of numbers, that yes, there exists a number called 1. That is a minimum number. Every number has a starting point, right? So he said there exists a natural number, 1. Okay, number 1. That is introducing the concept of what, the first number. So the first number 1. There exists a natural number 1. So now the theorem went forward and it says that every number has a successor. Every number has a successor. This may sound very, very vague, but what does this mean? When I say a number has a successor, what I'm trying to say is S of n, that is S of the natural number, is always a member of n. So S standing for successor, n standing for the next number, is always a member of what, natural numbers. What this means is that every number in a natural number has a next number. So if I have a number which is a natural number n, then there will surely be n plus 1. That is all. If I have a natural number p, then there will surely be p plus 1. That is the whole axiom. Then it's infinite. It's infinite. So the sequence of natural numbers starts from n maps to S of n maps to S of n, to infinity, and that gives us our infinite natural numbers. So I'll see you in the next lesson, where I'll introduce you to what we call whole numbers briefly. Then I'll take you through the subsequent ones. Don't forget to subscribe and follow the course orderly. See you.